7 hours. This means that Scuti is approximately 1,800 times larger in diameter than our Sun. If we convert this to volume, approximately 5 billion suns could fit inside Scuti. 5 billion. This number is so large that it ceases to have real meaning for our brain. But how can something so large even exist? To understand this, we need to talk about the life cycle of stars. When a massive star is born from a huge cloud of gas and dust, it begins its life as a bright, hot blue or white star. At that time, Scuti was probably a blue supergiant shining with incredible intensity. It was much smaller in size, but much hotter on the surface. Over millions of years, this star burned hydrogen in its core, converting it to helium through the process of thermonuclear fusion. This is the same process that's happening now in our Sun and that sustains life on Earth. But massive stars live fast and bright. Where our Sun will exist for approximately 10 billion years, a star with 30 times the mass burns out in just a few million years. When the hydrogen in the core runs out, something amazing happens. The star's core begins to compress under its own weight, heating up even more. This triggers a new stage of thermonuclear reactions. Now helium begins to burn, converting into carbon and oxygen. But here's the thing. When this happens, the outer layers of the star begin to expand. They expand and expand, inflating to incredible sizes. The surface temperature drops in the process. If previously the star's surface was heated to tens of thousands of degrees and glowed with blue-white light, now it cools to approximately 3,500 degrees Celsius. That's exactly why the star acquires a red color. This is still incredibly hot by human standards, much hotter than any furnace or volcano on Earth. But for a star, it's relatively cold. Don't let this coldness fool you. Although Scuti's surface is cooler than our Sun's surface, the total amount of energy it radiates is simply astronomical. Scuti shines approximately 340,000 times brighter than our Sun. If you replaced our Sun with Scuti, even at Earth's distance from the Sun, the temperature would be so high that our planet would instantly evaporate. Now let's talk about something that may seem paradoxical. Scuti is 1 billion times larger in volume than our Sun, but its mass is only approximately 30 times greater. How is this possible? The answer lies in density. The outer layers of Scuti are so rarefied that they can practically be called a vacuum. If you could fly through them in a spaceship, you wouldn't even feel particular resistance. This low density explains many things. First, gravity on Scuti's surface is actually weaker than on Earth's surface. Yes, you didn't miss here. On the surface of this giant star, you would weigh less than on Earth. This is because although the star's mass is large, it's distributed over such a huge area that the gravitational acceleration on the surface turns out to be smaller. This weak gravity also explains why the star loses matter so easily. Every second, Scuti ejects a huge amount of gas into cosmic space through stellar wind. This isn't the gentle stellar wind that comes from our Sun. This is a powerful stream of superheated plasma rushing into space at speeds of tens of kilometers per second. During a human lifetime, Scuti can lose mass equivalent to the mass of our Earth. Imagine this for a moment. An entire planet, all the material that makes up our world, is simply ejected into space as a byproduct of the star's aging. This matter doesn't disappear without a trace. It forms a huge nebula around the star, creating complex structures of gas and dust. These nebulae can stretch for light years in all directions, creating some of the most beautiful objects in space. The matter ejected by Scuti is rich in heavy elements. Inside this star, throughout its life, complex nuclear reactions occurred that created elements heavier than hydrogen and helium. Carbon, oxygen, neon, magnesium, silicon, sulfur, and many other elements were created here. When this matter is ejected into space, it becomes building material for future generations of stars and planets. This is one of the most important processes in the universe, the enrichment of the interstellar medium with heavy elements. When the universe was just born after the Big Bang, only the simplest elements existed: hydrogen, helium, and small amounts of lithium. Everything else, every carbon atom, every iron atom, every gold atom, all this was created inside stars. And it's giants like Scuti that play a key role in this process of cosmic alchemy. Let's dive a little deeper into what happens inside such a star. In the center, in Scuti's core, the temperature reaches hundreds of millions of degrees. At such temperatures, atomic nuclei move so fast that they can overcome electrostatic repulsion and merge together. This is thermonuclear fusion, the process that provides stars with energy. At this stage of its life, Scuti has long ago burned all the hydrogen in its core. Now helium is burning there, possibly even carbon. Each stage of thermonuclear burning requires higher temperatures than the previous one. Hydrogen begins to burn at 10 million degrees. Helium needs 100 million. Carbon, even more. And with each subsequent stage, the star produces increasingly heavier elements. First, hydrogen converts to helium, then helium to carbon and oxygen, then carbon to neon and magnesium, then neon to oxygen and magnesium, oxygen to silicon and sulfur, and finally, silicon to iron. Each of these stages lasts less and less time. Hydrogen can burn for millions of years. Helium, hundreds of thousands. Carbon, thousands. And the final stage, when silicon converts to iron, lasts only a few days or even hours. Iron is the end. It's the most stable atomic nucleus that exists. To create something heavier than iron through thermonuclear fusion requires not releasing energy, but expending it. When the star's core converts to iron, thermonuclear reactions stop. Suddenly, the radiation pressure that supported the star against gravitational collapse disappears. And then catastrophe happens. The core collapses in fractions of a second. Imagine this: an object the size of Earth, weighing more than our sun, compresses to the size of a small city in less than a second. The speed of this collapse reaches a quarter of the speed of light. This is one of the most violent processes in nature. The gravitational energy released during this exceeds all the energy the star radiated throughout its entire life. This collapse creates a shock wave that rushes through the star's outer layers. When this shock wave reaches the surface, a supernova explosion occurs. The star's brightness instantly increases billions of times. For several days or weeks, a single star can shine brighter than an entire galaxy with its hundreds of billions of stars. This is one of the brightest events in the universe. It's during this explosion that the heaviest elements are born. Gold, platinum, uranium, thorium. All these elements are created in the last moments of a massive star's life or during the merger of neutron stars. Every ring, every gold coin, every gram of gold on Earth. All this was born in the fiery hell of a supernova explosion that happened billions of years ago, long before our solar system appeared. But let's return to Scuti. This star hasn't exploded yet. It's still there, slowly pulsating, ejecting matter into space, living out its last millions or perhaps thousands of years. No one can say exactly when the explosion will happen. Perhaps tomorrow, perhaps in 1,000 years, or perhaps it has already happened and the light from the explosion just hasn't reached us yet. Remember, Scuti is located 9,500 light years from us. This means that the light we see from it now began its journey 9,500 years ago. At that time on Earth, the Neolithic Revolution was just beginning. People first started farming, domesticating animals, building the first permanent settlements. Writing didn't exist yet. The pyramids of Egypt weren't built. And a photon of light from a distant star had already begun its long journey through the galaxy to us. If Scuti exploded 1,000 years ago, we would only learn about it in 8,500 years. If it exploded yesterday, the light from the explosion would reach Earth approximately in the year 11,530. By that time, our civilization will either have long colonized other stars, or, let's hope this doesn't happen, will have disappeared from the face of the universe. But the light from the explosion will still arrive, regardless of whether there will be anyone here to see it. This is one of the strangest things in astronomy. We always look into the past. When you look at the moon, you see it as it was a second ago. That's how long it takes light to travel from the moon to Earth. When you look at the sun, you see it as it was 8 minutes ago. The nearest star to us, Proxima Centauri, is located at a distance of just over 4 light years. So we see it as it was 4 years ago. And when we look at distant galaxies through powerful telescopes, we literally peer billions of years into the past. Some galaxies we observe are so distant that their light began its journey to us when the universe was still very young, long before our solar system formed. We see these galaxies as they were in the early childhood of the universe. Perhaps some of them have long since disappeared, colliding with other galaxies or torn apart by tidal forces, but their ancient light still wanders through space. A telescope isn't just an instrument for seeing far. It's a time machine that allows us to peek into the universe's past. The farther we look, the deeper into the past we go. And this gives us a unique opportunity to study the history of space, to see how it changed over time, how stars were born and died, how galaxies formed, how the universe evolved from a simple and hot state immediately after the Big Bang to the complex, structured reality we see today. Returning to Scuti, let's talk about how astronomers actually measured the size of this star. This is not a simple task. Even the most powerful telescopes, Scuti looks just like a point of light. It's too far away for us to discern it as a disk, as we see, for example, the planets of our solar system. To measure the size of such a distant star, astronomers use indirect methods. One of the most important methods is based on measuring the star's brightness and temperature. If we know how much light the star emits in total and what temperature its surface is, we can calculate how large its surface must be. This works thanks to the laws of physics that describe how hot objects emit light. Stefan Boltzmann's law tells us that the amount of energy radiated by each square meter of surface depends on temperature. The hotter the surface, the more energy it radiates. If we know the star's total luminosity and its surface temperature, we can calculate the surface area and therefore the star's radius. But there's a problem. To know the star's total luminosity, we need to know how far away it is. If we're wrong about the distance, we'll be wrong about the size. Determining distances to distant objects in space is one of the most difficult problems in astronomy. Astronomers use the so-called cosmic distance ladder, a series of different methods, each of which works at a certain range of distances and is calibrated using the previous method. For the nearest stars, we use parallax, the change in the star's apparent position in the sky as Earth moves around the Sun. This is the same effect you see when you close one eye, then the other, close objects appear shifted relative to distant ones. But for stars thousands of light years away, this method doesn't work. The shift is too small to measure. For such distances, astronomers use other methods. One of them is based on studying variable stars, stars whose brightness periodically changes. For some types of variable stars, there's a relationship between the period of brightness change and their true luminosity. If we can measure the period, we know the true luminosity. And if we know the true luminosity and can measure the apparent brightness, we can calculate the distance. Another method uses interferometry. This is an extremely complex technique where light from a single star is collected simultaneously by several telescopes located at a great distance from each other. Then this light is combined in a special way, allowing resolution to be achieved that would be possible with a giant telescope the size of the distance between these telescopes. Imagine two telescopes located hundreds of meters apart. If you properly combine their data, you can get image clarity like a telescope with a diameter of 100 meters. Of course, in reality, everything is much more complicated. Atmospheric distortions must be accounted for. Observations must be precisely synchronized. Complex mathematical algorithms must be used to process the data. But the result is worth the effort. Thanks to interferometry, astronomers were able to directly measure the angular sizes of some of the largest stars in the sky. It's precisely thanks to the combination of these methods that we know Scuti is truly that large. Different research groups, using different methods, have come to similar results. This gives us confidence that our measurements are approximately correct, although there's always some margin of error and uncertainty. Interestingly, Scuti's size is not constant. This star pulsates, expanding and contracting over months or years. The amplitude of these pulsations is enormous. The star can change its radius by tens of millions of kilometers. It's as if our sun suddenly swelled to Mercury's orbit and then shrank back to normal size. And this cycle would repeat again and again. These pulsations are a sign of instability. The star is no longer in a state of equilibrium. Like our sun, complex processes are occurring inside it that periodically disrupt the balance between gravity, which tries to compress the star, and radiation pressure, which tries to expand it. Sometimes radiation takes the upper hand and the star inflates. Then gravity compresses it back, and so on again and again. These pulsations also affect the star's brightness. When the star expands, its surface becomes slightly cooler and it shines somewhat dimmer. When it contracts, the surface heats up and brightness increases. For observers from Earth, Scuti looks like a variable star. Its brightness fluctuates with a certain period. Studying these brightness changes gives astronomers valuable information about what's happening inside the star. Different types of pulsations correspond to different physical processes. Some pulsations are caused by oscillations of the star's structure itself, like sound waves propagating through a huge sphere of gas. Others are related to changes in energy transfer processes from the center to the surface. Scuti's atmosphere is a separate world, full of amazing phenomena. It's so thick and extensive that pressure and temperature in it change within enormous ranges. In the deeper layers of the atmosphere, closer to what we could call the star's surface, the temperature reaches several thousand degrees, and gas is in an ionized state. Electrons are torn from atoms, and matter turns into plasma. In the upper layers of the atmosphere, temperature drops and molecules can form here. Yes, even in a star's atmosphere, molecules exist. Astronomers have detected water, carbon monoxide, silicon dioxide, and other compounds there. These molecules form in relatively cool areas of the atmosphere where temperature drops below 2,000 degrees. Some of these molecules condense, forming microscopic dust particles. This dust consists of substances like silicates, the same minerals that make up rocks on Earth, or carbon in the form of soot. These dust particles are carried by stellar wind into interstellar space, where they can become nuclei for the formation of new dust grains and later planets. Think about this. Dust that forms in the atmosphere of a dying star can, billions of years later, become part of a new planet, perhaps even a planet with life. The cycle of birth, death, and rebirth continues on cosmic scales, connecting stars, planets, and ultimately, ourselves into one great whole. Scuti's magnetic field is another area of active research. Unlike our Sun, which has a relatively organized magnetic field with clearly defined north and south poles, Red Giant's magnetic field is much more complex and chaotic. This is related to turbulent movements of huge masses of gas in the star's convective zones. Convection inside a star resembles what happens in a boiling pot of water, only on scales that are hard to comprehend. Hot gas rises from the star's depths to the surface, cools, giving off its light into space, and then descends back down, where it heats up again. These convective currents can be millions of kilometers in size and carry as much energy as our Sun radiates in thousands of years. These movements also generate magnetic fields through a process called the dynamo effect. Moving electrically conductive plasma acts as a giant generator, creating and maintaining magnetic fields. But due to the chaotic nature of convection in red giants, the magnetic field turns out to be tangled, with multiple poles and constantly changing structure. This magnetic field plays an important role in many processes on a star. It can accelerate particles to high speeds, creating streams of energetic electrons and protons. It can form structures in the star's atmosphere, creating areas with elevated or reduced temperature. It also affects how the star loses mass. Magnetic fields can direct gas flows ejected by the star, creating jets or spiral structures in the circumstellar nebula. If we could somehow travel to Scuti and observe it up close, we would see a real cosmic show. The star's surface wouldn't be smooth and uniform. Instead, we would observe huge convective cells, brighter spots where hot gas rises from the depths, and darker areas where cooled gas descends back. Each such cell could be the size of our Sun, or even larger. Between these cells, we would see dark lines, boundaries where gas flows moving in different directions meet. On these boundaries, powerful magnetic fields can form, similar to how sunspots form on the Sun. But the scale would be much more grandiose. One such spot on Scuti could be larger than the entire visible surface of our Sun. Above this turbulent surface would stretch an atmosphere that gradually becomes rarefied, transitioning into cosmic space. There's no clear boundary where the star ends and space begins. It's a gradual transition. In this atmosphere, we would see dust clouds created by the condensation of molecules in cooler areas. These clouds could obscure part of the surface, creating an effect similar to clouds in Earth's sky, only much more dramatic. From the star's surface, huge prominences would constantly rise, arches of superheated gas stretching millions of kilometers into space, held by magnetic fields. Sometimes these prominences will become unstable and erupt into space, ejecting huge masses of matter. This will be similar to solar flares we observe on our sun, but millions of times more powerful. The star's color that we would see would depend on from what distance we're observing. From afar, UY Scuti appears deep red due to the low surface temperature. But as we approached, we would begin to notice different shades, some areas brighter and more orange, others darker and more red. The brightest hot spots could have a yellowish or even white color. And if we flew farther from the star and looked at it from a safe distance, we would see not just the star itself, but the entire system around it. A huge nebula of gas and dust would surround UY Scuti, creating a giant halo of light. This nebula is formed by matter that the star has been ejecting for thousands of years. It stretches for light years in all directions and glows with a dim reddish light, reflecting and scattering the central star's radiation. Interesting chemical processes occur in this nebula. Molecules that formed in the star's atmosphere continue to react with each other in interstellar space. Dust particles grow, attaching atoms and molecules from the surrounding gas to themselves. Increasingly complex chemical compounds are created, some of which are organic molecules, the basic building blocks of life. Yes, even in such it would seem inhospitable environment as the vicinity of a dying star, the chemistry of life is forming. Of course, life itself cannot exist here. Temperatures are too high, radiation is too intense. But the molecular building blocks that could become the foundation of life in the future are being created here and now. These organic molecules and dust will later become part of the interstellar medium. When a new stellar system begins to form millions of years later, these molecules will be included in the protoplanetary disk around the young star. Comets, asteroids, and perhaps planets will form from them. If the right conditions develop on one of these planets, these organic molecules can become the basis for the emergence of life. In a certain sense, life on Earth is connected to ancient stars similar to UY Scuti. The organic molecules that were delivered to young Earth by comets and asteroids come from the atmospheres of red giants that existed billions of years ago. This connection between dying stars and the origin of life is one of the most beautiful things in space. The death of one star gives life to another, and perhaps to an entire ecosystem of living creatures. Now let's talk about UY Scuti's future. As we've already discussed, this star is doomed to end its life in a grandiose supernova explosion. But what exactly will happen during this explosion? Let's go through the stages of this cosmic drama step by step, because this is one of the most impressive events in the universe. It will all begin with iron accumulating in the star's core. As we've already said, iron cannot release energy through thermonuclear fusion. It's too stable. When the core becomes predominantly iron, thermonuclear reactions will stop. Suddenly, the radiation pressure that supported the core against the pressure of the huge mass of the star's outer layers will disappear. The core will begin to collapse. At first slowly, then faster and faster. In fractions of a second, an object approximately the size of Earth, weighing more than our sun, will compress to the size of a small city. only about 20 kilometers in diameter. The collapse speed will reach 70,000 kilometers per second, almost a quarter of the speed of light. With such compression, matter density reaches incredible values. Atoms are literally crushed. Electrons are pressed into protons, forming neutrons and neutrinos. Matter transforms into what astrophysicists call neutron matter, a state of matter so dense that a teaspoon of such matter would weigh billions of tons. When the collapse reaches the point where density becomes similar to the density of an atomic nucleus, matter suddenly becomes incompressible. The collapse stops, and a powerful rebound shock wave arises. This wave begins to propagate outward through the star's outer layers at speeds of tens of thousands of kilometers per second. As the shock wave passes through the star's matter, it heats it to billions of degrees. At such temperatures, nuclear reactions occur that create heavy elements. It's here, in this fiery wave, that all elements heavier than iron are born: nickel, copper, zinc, and so on up to uranium and plutonium. In just a few seconds, more heavy elements are created than the star produced throughout its entire multi-million-year life. A few hours after the collapse begins, the shock wave reaches the star's surface and breaks out. At this moment, what we call a supernova explosion occurs. The star's brightness begins to grow rapidly. In just hours or days, it becomes billions of times brighter. At peak brightness, a single star can shine as brightly as an entire galaxy with hundreds of billions of stars. If this happened to Scuti now, and if we could observe this from Earth, of course, taking into account the 9,500 years it takes light to reach us, it would be an incredible spectacle. A new star would appear in the sky, so bright that it would be visible even during the day. At night, it could cast shadows like the full moon. This brightness would last for weeks, gradually fading over months. Ancient civilizations, if they observed such a phenomenon, would undoubtedly leave records of it. A new bright star would appear in the sky where nothing was visible to the naked eye before. Some cultures might perceive this as a sign from the gods, a prophecy, or a warning. Others might simply record the event in their astronomical records. Modern astronomers from around the world would direct all available telescopes at this supernova, collecting invaluable data about one of the most important processes in the universe. Matter ejected by the explosion would scatter in all directions at speeds of about 10,000 kilometers per second. This is about 3% of the speed of light. At such speeds, matter transforms into a giant wave rushing through interstellar space, sweeping away everything in its path. When this shock wave meets interstellar gas, it compresses it, heats it to millions of degrees, and makes it glow in the X-ray range. What astronomers call a supernova remnant forms, an expanding shell of superheated gas that continues to grow for thousands of years. One of the most famous examples is the Crab Nebula, a supernova remnant that flared up in the year 1054 and was documented by Chinese astronomers. The energy released during a supernova explosion is simply staggering. A typical supernova radiates in a few seconds more energy than our sun will radiate throughout its entire 10 billion year life cycle. Most of this energy, about 99%, is released in the form of neutrinos, elementary particles that almost don't interact with matter and simply fly through everything. Neutrinos from a supernova explosion can pass through the entire thickness of the star, through planets, through everything, practically without being delayed. They carry a huge amount of information about what's happening in the very heart of the collapse. When the supernova of 1987 flared up in the Large Magellanic Cloud, neutrino detectors on Earth recorded several dozen neutrinos from this event. This confirmed theories about the mechanism of supernova explosions and opened a new era of neutrino astronomy. But what remains after the explosion? In the center of the supernova remnant, a compact object forms, either a neutron star or a black hole. For a star with the mass of Scuti, which weighs approximately 30 solar masses, the result depends on many factors. If during the explosion the star loses enough mass, the remaining core can become a neutron star. If not, a black hole will form. A neutron star is one of the strangest objects in the universe. Imagine mass greater than our sun's mass, compressed into a sphere with a diameter of only about 20 kilometers. The density of such matter is so great that a teaspoon of neutron matter would weigh 1 billion tons. This is approximately the mass of Mount Everest in the volume of a teaspoon. Gravity on a neutron star's surface is billions of times stronger than Earth's. If you somehow found yourself on a neutron star's surface, you would instantly be flattened into a layer of atoms fractions of a millimeter thick. But even if you somehow withstood this gravity, you would be killed by intense radiation. Neutron stars have super powerful magnetic fields, trillions of times stronger than Earth's. These magnetic fields accelerate charged particles to speeds close to the speed of light, creating beams of intense radiation emanating from the star's magnetic poles. If the magnetic axis doesn't coincide with the rotation axis, and this happens in most cases, these beams rotate with the star like lighthouse beams. When such a beam is directed at Earth, we see a brief flash of radiation. Such objects are called pulsars. Pulsars rotate extremely fast. Some make hundreds of rotations per second. This means that an object with mass greater than the sun and the size of a city is spinning so fast that its equator moves at a speed that constitutes a significant fraction of the speed of light. The precision with which pulsars emit their pulses is impressive. Some pulsars are more accurate than the best atomic clocks created by humans. If after the explosion a core with a mass greater than approximately 3 solar masses remains, even neutron matter pressure cannot resist gravity. The collapse continues and a black hole forms, an object so dense that even light cannot escape from its gravitational field. A black hole is perhaps the most mysterious object in the universe. At the center of a black hole, according to our theories, there is a singularity, a point of infinite density where all the laws of physics we know cease to work. Around the singularity is the event horizon, a boundary beyond which nothing can return. Everything that crosses the event horizon is forever lost to the outer universe. But even black holes aren't completely black. British physicist Stephen Hawking showed that black holes emit very weak radiation through quantum effects near the event horizon. This Hawking radiation is so weak that it's practically impossible to detect for stellar black holes. But theoretically, it means that black holes very slowly evaporate. For a black hole with a mass of several solar masses, the evaporation time is approximately 10 to the power of 67 years, a number so large that the current age of the universe looks like a moment compared to it. Around the black hole or neutron star formed after the supernova explosion, the supernova remnant continues to exist, an expanding nebula of gas and dust. This nebula contains all the heavy elements created during the star's life and during the explosion. It mixes with interstellar gas, enriching it with elements necessary for the formation of the next generation of stars and planets. And so the cycle continues. New stars form from the enriched interstellar gas. Planets form around these stars from the same gas and dust. Some of these planets turn out to be in the so-called habitable zone, at the right distance from their star, where liquid water can exist. On some of these planets, with the right combination of conditions, life can arise. And this life is literally composed of elements created in past stars. Every carbon atom in DNA molecules, every calcium atom in bones, every iron atom in blood hemoglobin. All this was forged in the nuclear furnaces of stars billions of years ago. When famous astrophysicist Carl Sagan said, "We are made of star stuff," this wasn't a metaphor. This is a literal scientific truth. Think about this for a minute. The atoms in your body have gone through an incredible journey. They were born in the heart of a star billions of years ago. Survivaient à Supernova explosion. Drifted in interstellar space for millions or billions of years. Became part of the gas cloud from which our solar system formed. Were included in the protoplanetary disk around the young sun, became part of Earth. Participated in the geological cycles of our planet. Perhaps were part of rock, then were released by erosion, became part of the ocean, were absorbed by a living creature, returned to the soil. And finally, through a complex chain of biological processes, ended up in your body. And this journey isn't over yet. When you die, the atoms of your body will return to the environment. Some will become part of other living creatures. Others will return to the ocean, atmosphere, soil. And in billions of years, when our sun becomes a red giant and swallows the inner planets, these atoms may be ejected into interstellar space. Perhaps in uncountable billions of years, they will become part of a new star, a new planet, perhaps even a new form of life that we cannot even imagine. This is the true beauty of space. Everything is connected. Everything is part of one great cycle. Stars are born, live, and die, but their death is not the end. It's the beginning of something new. Every star that explodes seeds the cosmos with elements for future worlds. Every planet that forms carries within it the legacy of long-dead suns. Scuti, this enormous red star where light travels 7 hours around its surface, this isn't just an astronomical curiosity, not just a number in a catalog. This is a living participant in the cosmic drama that has been unfolding for billions of years. It was born from gas enriched by previous generations of stars. It lived its bright life, converting simple elements into complex ones. And when its time comes, it will return all this back to the universe, giving the possibility for new worlds to be born. And we, humans, stand here on our little blue dot and look at the sky. We are small, so small that it's hard to even imagine. Our planet is just a speck of dust in space. Our sun is one of hundreds of billions of stars just in our galaxy. And our galaxy is one of trillions of galaxies in the visible universe. Against such scales, we seem absolutely insignificant. But there's something beautiful in this. These tiny creatures who live only a few decades on a small planet near an ordinary star, have been able to understand the universe. We built telescopes that allow us to see billions of light years away. We developed mathematics and physics that explain how stars work. We understood our origin, our connection with the stars. We learned that we're not just observers of the universe. We are its part. We are its children. Every time you look at the night sky and see the twinkling of stars, Remember UY Scuti and other giants hiding in the darkness of space. Remember that there, far beyond what the eye can see, exist worlds so magnificent that our mind can barely comprehend them. Stars where light needs hours to orbit them. Neutron stars where mountains are millimeters high. Black holes where time and space are warped to infinity. But also remember that you are made of the same matter as these stars. That every breath you take contains atoms that were once part of distant suns. That you are not separated from space, but its integral part. The universe doesn't just exist around you. It exists in you just as you exist in it. 7 hours of light around UY Scuti. 14 seconds around our sun. These numbers tell a story about diversity, about beauty, about the incredibility of the universe in which we live. But the greatest wonder is not in the size of these stars, not in their power or brightness. The greatest wonder is that we can understand it, that we can look at the sky and see not just points of light, but entire worlds, stories, the future. Thank you for being with us today on the Quesaria channel. Thank you for spending time to learn about one of the most amazing objects in our universe. Continue to wonder, continue to ask, continue to look at the stars. Because it's exactly this, the ability to wonder and strive to understand, that makes us human. It's exactly this that elevates us above mere existence and gives our life deeper meaning. Space is vast, mysterious, and incredibly beautiful. And each of us has the privilege of living in an era when we can not just look at it, but truly get to know it. Like it if you enjoyed this cosmic journey. Subscribe to the channel so you don't miss our next discoveries. Write in the comments what you want to learn about in the next episodes. And remember, when you look at the stars look at you. Because you are made of them, and they live in you. We are all one big cosmic family, connected through space and time by threads of stardust. See you in the next video, friends. Clear skies to you and endless curiosity. Quesaria says goodbye to you. Keep dreaming about the stars. Hello, friends. You're on the Quesaria channel. And today we'll talk about the true monsters of the universe, about objects so enormous that our mind simply refuses to comprehend it. Imagine a star so large that light needs 7 hours to orbit it. 7 hours. For comparison, light orbits our sun in just 14 seconds. Today we'll dive into the world of hypergiant stars and find out how something so incredible can exist in our universe. Let's start by trying to imagine the scale. Our sun seems huge to us, right? It gives us light, warmth, life. Its diameter is approximately 1,400,000 kilometers. This means that over 1 million Earth-sized planets could fit inside the sun. Impressive, isn't it? But wait, this is just the beginning of our story. Now meet UY Scuti, one of the largest objects humanity has ever discovered in the universe. It's a red hypergiant, located approximately 9,500 light years from us in the constellation Scutum. And here's what truly staggers the mind. The diameter of this star is so large that if we placed it in place of our sun, its surface would reach Jupiter's orbit and possibly even further. Mercury, Venus, Earth, Mars. All these planets would simply disappear inside this star. Let's try to comprehend these numbers through the speed of light. Light travels at an incredible speed, approximately 300,000 kilometers per second. At this speed, you could circle the Earth 7.5 times in 1 second. It's so fast that we can't even truly imagine it. And even at such a fantastic speed, light needs a full 7 hours to travel along UY Scuti's equator. 7 hours of continuous travel at the speed of light. Compare this with our sun. A ray of light orbits our sun in just 14 seconds. 14 seconds versus 7 hours. This means that Scuti is approximately 1,800 times larger in diameter than our sun. If we convert this to volume, approximately 5 billion suns could fit inside Scuti. 5 billion. This number is so large that it ceases to have real meaning for our brain. But how can something so large even exist? To understand this, we need to talk about the life cycle of stars. When a massive star is born from a huge cloud of gas and dust, it begins its life as a bright, hot blue or white star. At that time, Scuti was probably a blue supergiant shining with incredible intensity. It was much smaller in size, but much hotter on the surface. Over millions of years, this star burned hydrogen in its core, converting it to helium through the process of thermonuclear fusion. This is the same process that's happening now in our sun and that sustains life on Earth. But massive stars live fast and bright. Where our sun will exist for approximately 10 billion years, a star with 30 times the mass burns out in just a few million years. When the hydrogen in the core runs out, something amazing happens. The star's core begins to compress under its own weight, heating up even more. This triggers a new stage of thermonuclear reactions. Now helium begins to burn, converting into carbon and oxygen. But here's the thing. When this happens, the outer layers of the star begin to expand. They expand and expand, inflating to incredible sizes. The surface temperature drops in the process. If previously the star's surface was heated to tens of thousands of degrees and glowed with blue-white light, now it cools to approximately 3,500 degrees Celsius. That's exactly why the star acquires a red color. This is still incredibly hot by human standards, much hotter than any furnace or volcano on Earth. But for a star, it's relatively cold. Don't let this coldness fool you. Although Scuti's surface is cooler than our sun's surface, the total amount of energy it radiates is simply astronomical. Scuti shines approximately 340,000 times brighter than our sun. If you replaced our sun with Scuti, even at Earth's distance from the sun, the temperature would be so high that our planet would instantly evaporate. Now let's talk about something that may seem paradoxical. Scuti is 1 billion times larger in volume than our sun, but its mass is only approximately 30 times greater. How is this possible? The answer lies in density. The outer